Okay, good morning again. So we are here for a real treat. We have an excellent talk here by Professor Laurent Najman. He did his PhD in applied mathematics from Paris-Est University, and then he worked in a variety of places. One of them is Central Research Labs of Thompson, CSF, and where he was the Director of Research and Development. And he also joined the animation science, where he did excellent work that won him some of the best prizes and awards, one of them being the European Information Technology Prize in 1997 and the Hottest Products of the Year in 1996. And then he actually worked with OCE Print Technologies, where he did various problems on image analysis dedicated to scanning and printing. So as you can see, he has a vast, diverse set of expertise that he's going to draw from on this talk, and I hope you all get a lot out from his wisdom. He's currently a professor in the informatics department in ESIEE, and his research interests are in discrete mathematical morphology and discrete optimization. And today he's going to talk on morphological filtering in shape spaces. And with that, I welcome Professor Najman and to share his ideas with us.
So, another important reason to be happy is that there are few countries in the world where mathematical morphology, my main research field, has taken deep root, and Brazil is arguably one of the largest and the most important one. So I do expect that most of you, if not all, knows some basic mathematical morphology as dilation and erosion, which in a sense for me is reassuring. If you do not know what is a dilation, this is not a problem. I expect you to understand my talk. But if you do know what a dilation is, at least we share some common knowledge, and I can start from that. So the motivation of the goal today is image filtering and how to obtain such a result from a given input image. What you can notice here is that we remove from the input image everything that is not round. So it's a kind of erosion, or I don't know, filtering, in which you preserve the shape of the object, the shape being defined in a quite loose way by an energy function or an attribute or something like that. So intuitively what I want to do is to work with structuring elements, as in mathematical morphology classically, but being able to deal with structuring elements that do not have a fixed shape and to obtain such results. Okay, so the plan of the talk is the following. The route are taken into connected filtering. So I will first describe what connected filters are, and then I will describe the novelty, which is shape-based morphology. And then I will illustrate the work with various images taken from different applications before concluding. So first, connected filters. So one interesting direction in research is to try to find alternative representation to what an image is. The most classical one, I believe, is Fourier transform, functional decomposition, in which from a given image, this one is better, I think, because both sides you do have the mouse. So you have the phase and the amplitude, and you can analyze and find easily in this other representation of the image, equivalent representation. Some artifacts are present, some things are can be easily found in this image, its representation. But there are plenty of other. We can think of multi-resolution decomposition, looking at an image at various sizes, for example, or multiscale, in which you're trying to give for it a pixel, a region around it, according to a scale, but each pixel has different scales to which you can look at it. Or the representation that we will deal more specifically in this talk are the last two ones. So this is threshold decomposition. Threshold is the most basic operation in image analysis, I believe. So you take the whole stack of threshold. And hierarchical representation by grouping pixels according to some rules, from the pixels themselves to large regions, the higher level in the hierarchy being the whole image itself, just one region. Okay, they are all very good representation, and you can mix them, you can do whatever you want with them. The choice is driven by the application needs, and you can do whatever you want with those. This is not the problem here. Okay, so what I'm going to look at are connected filters. Connected filters are filtering tools that merge flat zone with the same color or the same gray level. The main properties are they do not introduce new contour. When merging flat zone, you just remove contours, but you do not change the position of the contour, so the contour will be exactly the same before and after, maybe less contour in the results. One example is the leveling. It's the leveling preserve order between neighboring pixels. So if the center pixel is greater than a neighbor, you will have the same in the results. Well, it's not correct here, but not a problem here. The formula are not correct here. But anyway, on this example, for example, you have the red function in F and a marker function H, and what you want to do is simply removing some blobs that are not marked by the H function. So you have remove a white blob and a black blob here, and preserving everything else in the image. And basically, well, this is just an example, but we're going to see how to implement and to deal with those kind of filters. One popular implementation relies on a tree representation, and there is a nice review that appears in Signal Processing magazine recently. Well, you start from the image, you build a tree from it. For example, the tree of, well, we're going to see exactly what kind of tree you can build on this image, but the tree is equivalent to the image. That's the important point. From the tree, you can reconstruct the image. And then you do the filtering not on the image itself, but on the tree. So you remove some nodes of the tree, so you obtain a second tree, and you reconstruct the image from this simplified tree. Okay. Here is one example. So it's a 1D signal here. You have on the x-axis and the y-axis, F. So the signal is in blue. Okay, you can take a threshold. At a given threshold, you have two connected components in red. Okay, very good. You can vary the parameter of the threshold, of course, and you can obtain a tree from that. Okay, you at altitude 5, you have this connected component. For these two connected component, 3 these two connected component, 2 this connected component, 1, okay, and 0. So plenty of connected components. The nice thing is that this connected component, well, they are either disjoint or nested. So you can build a graph from this connected component, actually a tree. The edge that you've added here, that we have added here, and they represent the father-son relationship, the inclusion relationship. If you have an edge, that means that one of the node is included in the other. So this is a tree here. Okay, there are plenty of trees that we can build from the image. We've just seen the max tree. On this image, this example here, the max tree is very simple, just a straight line. But the tree of the minima is a bit more complicated. You have two minima, D and E, in black at altitude 0. And okay, one root. There, another interesting tree is the tree of shapes that you can imagine as a tree of level lines. You just draw all the level lines, and for example, the level line of B include these two connected components here. So the shape of B is B union A union E, and you can do that, you obtain another tree. So you can think of it as a tree of level lines. With respect to these two trees, it's an autodual tree in the sense that you don't, you process black and white in the same sense. Here, the two leaves, in this tree, the leaves are either maxima or minima. Here, the leaves are both minima and maxima. But you can generalize and take any kind of merging tree. Here it's a binary partition tree. You just divide your image according to some kind of superpixel, and you merge them according to some rule, whatever, and you have a true representation of your image. Very classical. Okay, is that clear? Please, if you have any question, don't hesitate to ask during the talk. So, once you have the tree, what can you do with that? You can filter, and to filter you need a rule. So here it's an attribute. For example, I take this connected component in red. What can you imagine? Plenty of things. For example, nice sound. I don't know how you do that, but here it's the area, simply the number of pixels of this component. You can have the 8, the difference between the highest pixel and the current level, or the volume, the number of pixels contained in the connected component and in the shape of the function itself. Tree attribute. And okay, these three attributes, they are increasing in the sense if the connected component is included in another component, the attribute of the first one is lower than the attribute of the second one. But in general, most shape attributes, they don't have this property, which is very nice. But unfortunately, most of shape attributes don't have this property. So other attributes are, for example, kind of circularity. Circularity is the area divided by the p times the square, the length of the contour. So that's one for a circle. Or round object can be also found by by the first attribute. You can also look at elongation, like taking for example, you take a best fitting ellipse and you measure the differences. You estimate the ratio, so that gives you a measure of how long an object is. Okay. They are not increasing, but they are very interesting. Okay, if you have an increasing attribute, it's easy to filter. Why? Because it amounts to remove the components you don't want. For example, if you want to remove every connected component with a volume of lower than 5, okay, you have 2 here for this component. Here 3, 2 plus 3 is 5. You will remove this one and this one also, and okay, you remove. So it's easy. It's just you remove the connected component from the tree. Here is an example. It's a real example, part of a big application. This is ancillary, a kind of ancillary cells with small things that move, and they are responsible for the placement of the organs in the body. And in some rare disease, the cells don't move, and you can have the heart on the other side of the body and give you problems. Well, anyway, if you look at the maxima of the first image here, you have plenty of those maxima, but you can filter the image with volume criterion. You don't see much difference, and there are not so much difference, but actually this is a very good simplification steps are the maxima of this image. This is a good pre-segmentation at least. So, very good filtering tool. The question is that if you want to process a non-increasing attribute, you don't know how to do that. Well, people have, well, yeah, not yet. If an attribute is increasing, you just print the leaves. It's just threshold the attribute. But if you want to deal with non-increasing attribute, you have several routes that amounts more or less to threshold, either by removing the whole branch according to a rule. If you don't want a node at a given level, you remove also all the sons, all the branch to which the nodes belong, according to some rule. You can do simple thresholding strategy, also removing the nodes that you don't want by thresholding, but as we'll see later, it's not very convenient in some cases. What we'll do is a bit more elaborate, and this is the most important point in the talk. So wake up. Because I will reapply the same process on the graph. So generally, this is where people get confused, because from the tree, I build a tree. Hey, what's happening here? Well, you can see the tree as a graph itself. It's a graph. And you can value the tree, the node of the tree, with whatever you want, whatever kind of attribute. Well, it's in that case, you have a graph with neighbors. The neighbors relationship is simply whether you are a son or a father, so parenthood relationship, and give you a kind of neighborhood. So once you have this kind of neighborhood, you can apply any kind of graph algorithms on that tree, on that graph. So you can build a tree on the first tree. I will show you some example, but that's mainly the most complicated point. So, and this is how we do shape-based morphology. Okay, here is a very simple example, a tree in which you have nodes, and the nodes have an attribute that is whatever you want. It's not increasing. So in this tree, you can threshold this graph. So here is the connected component at level less than 4. There is only one node. At level 5, there is 2 connected components. At level 6, the node G merge with the node C, and you still have 2 connected components, but this node has merged with his son. And so you can continue. At level set, you have this node here, and so 1 connected component, and 8, and so on. So from the connected component, you can build a second tree. Take the mean tree here. So here, the component G merge with C, F and C merge with H, and this is only the resulting node here. It's H is H union C union G union F, and so on. Is that clear? Because I can go on this a second time if you want, because this is the most complicated part. I will do that. So you are just building a tree of minima on a graph. This graph happens to be a tree, but you don't care. You just see as a planar graph here in this case. So the 2 leaves here. This is the connected component below 5. Will be the leaves of the tree, and G is contained in G union C here, and then in this tree, and so on. Okay? What have I done here? I've transformed the first image into a graph. Whatever is this graph. Here I will work only with trees, but this graph is a tree, okay? And then all the algorithm I'm dealing, the graph is equivalent, this tree is equivalent to the first image. So that's fine. With this tree I can reconstruct the image, but I will not work on the image space, I will work on the tree of shapes, because each node is a shape. So they are organized in a shape space. The relationship, neighborhood relationship, is the parenthood relationship, and I will work on this space of shapes to do things. And the first things I'm going to do is simply reapplying the same process in the space shape, in the shape space. Clear? Okay. This is good because it generalizes the classical attribute filtering. If the attribute is increasing, the mean tree of the first tree is the same, exactly the same tree. So you don't have to ask the question whether or not the attribute is increasing. You don't care. You just apply the process, whatever it is, and you don't change anything if the attribute is increasing. So you do work that is not useful, but you're doing what's usual. You can also find the attribute thresholding, because attribute thresholding is simply finding the leaves. Pruning the second tree is simply attribute thresholding. But you can do shape filter on the second tree, and in this case you obtain nice filters, meaning that the transform, if you work with a max tree, you preserve the infimum relationship, so it's a lower leveling. If you work with the mean tree, the tree of minima, of minimum mean threshold, you preserve the superior relationship. So it's shape-based upper leveling. This has never been before. This is the first time I'm showing that. And if you work with a tree of shapes, this is a totally new kind of filter, because this filter is autodual, meaning that you process black and white in the same way, and it's self-dual, okay? And it's not anymore leveling, because you don't guarantee anything before and after, but it's a connected filter, and we call that kind of connected filter morphological shaping, which is, I like this word, morphological shaping, it's shape. Well, anyway. Okay, how do you use that? Here is an energy function here. You have A, B, C, 2 minima, that you can order. Here, for example, A is lower than C and lower than B. This order is arbitrary, it depends on what you want to do. What I choose here is finding the altitude, and I say that a minimum is lower than another minimum if the altitude is lower. But you can choose other criterion. And so when you filter, for example, you can compute the altitude of this minimum, and you say that B will merge with C, and then C will merge with A, because it will merge with the phasor. So at this altitude, when you fill, imagine you fill the image with water. At this level of water, here, the basin of B is filled. It diverges in C, so it merges with C. You continue to add more water, and then C is going to A. Okay. So you can attribute an 8 to each one of those minimum, and that give you a second attribute to filter the tree and preserve the blobs that are the most meaningful. So B here is less meaningful than C, that is itself less meaningful than A. Here I've used as attribute the altitude, the height, but you can use, once again, any kind of attribute on that second tree. Is that clear? Okay. So first application to object segmentation. Well, this looks like very complicated. It's a bunch of formulae, but actually it's very simple in principle. It's an energy that is more or less inspired by Mumford and Shah or Snake's energy. You have three terms in this energy. Here, this V here measure how different you are from the mean of the function. So here, these terms, here it's simply the variance. Here it's kind of variance of variation. And here, these terms tells whether you prefer to merge these two regions, take the union, or keep them separated. Here, it's simply a term that say that you want something more or less with more or less curvature, more or less agitated. And here is something to prevent small objects. But basically, that's Mumford-Shah energy. Okay. It's very complicated to optimize such a kind of energy, of course, because it's not non-convex. But well, nice thing is that you can do that quite easily if you look at your trees. So, okay, here it's the energy in a branch of the tree. Starting here, that's the leaf, the pixel itself. Here it's the root of the tree, and you can see how the energy behaves along a branch of the tree. And yeah, you see that very low way. Here in green it's simply the snake energy. In blue it's the novel energy we introduce here. And you can see that this energy is better than the snake in the sense that the minima of this energy are more easily, you can find them more easily. And they are better accentuated. So the first minimum here that is very important in the sense described before is B. It corresponds to this on this very simple image. That's the inner circle. We're working here on the tree of shape, so autodual. And the second important minimum here is the external. Okay, so the significant minima, well, it's easy to find the minima of this energy on the tree. It's a linear process, but you can order them and find objects in the tree, good curves in the tree, significant curve. Okay, so you can do filter with that. Filtering is simply you do a closing, meaning you get rid of spurious minima, and so you keep only the interesting minima, and it's a closing in the morphological sense. So you can do a closing with any kind of attribute. It generalizes also something called MECR, maximally stable extremal region. This is something well known in computer vision. It's something that find interesting shape in the image, and that they are used after that for doing kind of matching or registration of image. But the MECR are defined on the min tree, I think, or the max tree. So you can do MECR on the tree of shapes, so it's autodual, and you can use any kind of criterion. The one that is used in MECR is ratio of area of nodes, but Okay, why not? It's a good criterion, but you can use any tree, any kind of attribute, and so do a lot of experiments with that. We haven't done those experiments, but you can, just the beginning, but okay. Okay. So, before showing some more examples, I just want to introduce saliency map, which is a kind of, well, we'll see. Well, from an image, you can obtain a set of segmentation. Here it's simple segmentation, watershed, I believe, and merge the contours according to some criterion. Great. When you merge regions, you have less contours, but the nice thing is that the contours, they don't move. And so you can stack those contours. And the more the contour stays in the hierarchy, the longer it stays, the more visible it is. And you can see the more robust it is to variation, to change in the setting of your parameters. So this kind of map summarizes all segmentation depending on one parameters that you can obtain by varying the parameter. Okay, so there exists a nice theorem that says that these maps are equivalent to the dendrogram, classically used in classification, and they condense all the information, and they can be defined as a kind of watershed.